It's question show time. Your questions, my answers. As always, wherever you are, anywhere on my channel, if a question pops in your brain, I'll gather them up and I'll answer them here. Now, I've had a couple of people say to me, how come you didn't answer my question? And there's a few reasons. One is I get thousands of YouTube comments every week across the channel. So, and a lot of the times I'm looking for the questions that are, that I haven't answered before. And they're fairly short, so that it's not like I don't want to like read out a big long essay. So something that's short, something that maybe, you know, if you've watched a bunch of the question shows and there's something that's fairly new, like a new idea, or something that just I haven't covered before, that would be great. And so those are the ones that I tend towards. So it's not personal. All right, let's get into it. Ido Deckers. Hey Fraser, how much time would it take to clear Leo of all the junk naturally if we don't send any more junk? Is it a few years, tens, or hundreds of years? It all depends on how high the space junk is orbiting. So a good example is like the International Space Station. Not that it's space junk. It's orbiting at like 400 kilometers above the Earth. And it is constantly being pulled back down to the Earth because of the drag through the atmosphere. And so they launch the Soyuz capsules, they deliver astronauts and cosmonauts, and they also use the Soyuz and the Progress to raise the altitude of the International Space Station. So if they didn't do that, the space station would just come back to Earth, and it wouldn't take long. Another good example is like the new Starlink satellites that SpaceX has launched. They will probably re-enter the Earth's atmosphere within just a couple of years, like 3 to 5 years on their own, without any modifications. So stuff that's very low, it's going to come back right away. And so that's not the risk. And so people are really concerned about, say, the amount of space junk that's going to happen from these low Earth orbiting internet satellites. And there's really very low risk. They will orbit on themselves. If they die, they'll crash back into the atmosphere very quickly, and the atmosphere will be clean, or the low Earth orbit will be cleaned of space junk just within a couple of years. The stuff that's the problem is the stuff that's higher, at higher altitudes. So now you're looking at, say, 1,000 kilometers altitude and above. And for some of those, you're exactly right. They're going to take decades. They're going to take hundreds of years. And if you go even higher than that, they're going to take thousands of years, tens of thousands of years. And there's this sort of nasty sweet spot where you're going to have stuff that's very high, so it's really not going to come back down in our lifetimes, but it's close enough and packed enough that it can smash into each other and create this shell of material that would lock us away from space for thousands of years. So that's the risk. That's what people are concerned about. And that's what we need to try and figure out some solutions to deal with it. Jeff. Now I have a question. With the problem of space junk, why don't the nations of the world come together and fund to clean up space? They could launch those junk-capturing probes that force the junk to burn up in the atmosphere. They could put those on Falcon 9s or perhaps piggyback on a ride when they launch new satellites. I might have to stop you at the nations of the world coming together to clean up something. I mean, I guess it's happened in the past, right? The nations of the world have come together to stop releasing chlorofluorocarbons, which was damaging the ozone layer. But we're dealing with this issue of global warming, of climate change, and trying the entire world needs to come together to reduce its carbon emissions. So, and that's not going so well. So, I mean, dealing with space junk, sure, yeah, you could have all the nations of the world come together and make some fairly rigorous rules about how to deal with space junk. And you need to sort of have an end-of-life strategy for anything that you send into space. So right now, satellites are sent into space most of the time, and no one is really concerned about what happens when they're dead. The upper stage booster rocket that carries the satellite into orbit, often they end up in some big orbit that's going to be going around the Earth for tens, hundreds, thousands of years, and no one's super concerned about that. So I think that as more and more of these satellite networks get launched, as more satellites go up, as more rocket companies happen, this is going to get more and more important, and countries are going to take this more seriously. And we're probably going to move to this model where anyone who launches a rocket, anything into space, has to demonstrate how they're going to get rid of it when their mission is done, or it's not going to be approved. That's going to be the future. How do we deal with the stuff in between? I mean, we've done a whole episode about this. It's probably time for an update. You can launch things that will grab or deal with space junk on like a Falcon 9 rocket. The challenge, as I mentioned this before, is that almost every satellite, every piece of junk, and there are tens of thousands of these pieces of junk, are on a relatively individual orbit. So you have to make a spacecraft that can intercept one, somehow use propellant to move to a different orbit, intercept another piece of space junk. There's lots of great ideas. You can shoot them with a harpoon, you can catch them in a net, you can attach a solar sail, like a drag sail to them, and it'll pull them back into the atmosphere. Probably the best idea, the one that I like the best, is the one of sending up or using some kind of laser system, either an orbital laser system that will shoot these pieces of space junk. And as it does, it vaporizes a tiny little bit off of the satellite, and that acts like a thruster. And so the laser, what's great about this is the laser can shoot at different targets at whatever is the right time and impart tiny little thrusts on all of these different pieces of space junk and bring them all back down. So my hope is in the next few decades, one of these laser systems gets put into space. And maybe you could also use it to send the breakthrough Starship off to Alpha Centauri. The challenge, of course, is who wants to have an incredibly powerful laser system in space capable of bringing down satellites? It's possible that the various nations would not agree on that. So, big problem. It's going to get worse in the future. Hopefully people will figure out a way to come together, just like climate change. Luis Tapia. Hey Fraser, really love your show. I was wondering if in the future someone would want to advertise on the night sky, like the concept of how we can see certain satellites in the sky already. Do you think this is possible if somebody is bold enough? Thank you. It's possible, but why would you want to do that? Why would you want to advertise in the night sky? Like, we've got advertising everywhere else. They're in our dreams. So no, I do not want, like, don't, stop even thinking about it. Stop the proposal. Now, the reality, of course, is that people have already thought of this. There's a Japanese company that is able to generate shooting stars for your party on demand, which is a terrible idea. Kind of cool, but no, it's a terrible idea. And then there's this Russian company that was proposing to put up satellites that would kind of act like pixels in space. So they would furl and unfurl like a mylar sheet in space, and then it would be able to spell out letters. And there's been ideas for putting billboards, and there's been these various satellites that are like an art installation that people have proposed to go to space. But no, I think like we're already having a big argument about even sending the Starlink constellation and these other internet satellites to space. And their only job will be to provide internet to the 3 billion people on Earth who don't have access to the internet right now. So you kind of got to weigh the pro and the con. But there is no pro to putting stuff in space that's purely to take away the beauty of the night sky. So no thank you. Please don't. No. Guyup2K. Question, why is panspermia appealing as a hypothesis? Why don't we just settle for the we can't find the ancestor on Earth, it's likely its archaeological traces were erased by time or we didn't look well enough? Why the extra step of life probably came from elsewhere, knowing that we'll probably never be able to prove it? Is life originated from Earth troublesome enough to justify assuming it came from another planet? It's not that it's impossible to come up with an answer for this. If we discover some kind of life form on Mars, for example, thanks to, say, the Mars 2020 rover, which is going to be equipped with the ability to sense the conditions for life, maybe some of the byproducts of life. So it's sort of the best tool that's been sent to Mars so far. But there's sample return missions on their way to Mars. And in the future, you can imagine there's going to be human explorers that are searching Mars, like they're looking on Mars. And they're going to be trying to look for life. And then the question is, right, if they find life, did that life form on Earth and then somehow move to Mars? Did that life form on Mars and then somehow move to Earth? Or did that life independently form on Earth and Mars? All three of those options is amazing, right? And if they don't find any life on Mars, that's also amazing. So every possibility of what they can discover is incredible. And so I don't see why you have to constrain what you're looking for, right? Until you find definitive evidence that something appears to be one way, why be closed-minded about it? You just look, you just follow the evidence wherever it takes you, and you follow your curiosity, and you just keep asking questions until you feel like you understand the answers as well as you can. So I don't see why, someone came up with an idea and said, hey, here's something interesting. It looks like meteorites can survive the journey, or life inside a meteorite can survive the journey from one planet to another within the solar system. And what that means, the implication for that is that, hey, maybe life could make this journey. It's an interesting idea. Let's find some evidence. And if we don't, then maybe it's not true. But I don't know. Doesn't hurt to look. Josh M. Hey Fraser, would you like to see a manned space station dedicated entirely to astronomy? It could survive on its own and be operated remotely, but maybe twice a year astronauts service the station. It has a small living quarters enough for a month's stay. Unlike James Webb or Hubble, if it breaks down or needs to be boosted, it can be done easily. I don't think that we need to have a crewed space station that its purpose is to be a telescope. We've got, say, the Hubble Space Telescope, which has been operating for 30 years now. Apart from that problem in the beginning, it's been really good. It's completely robotic, just does its job, and every now and then the astronauts went up and upgraded some of the instruments and tuned it up. So, I mean, it's not like you need astronauts to kind of look through the eyepiece in a space station telescope. Big, like telescopes, space telescopes, they're just robots. They're just like robotic spacecraft, except their job is that they're a telescope. And I think that's the right way to go. You launch a telescope, it does its job. At the end of its mission, when you think about how much it costs, even just to service the Hubble Space Telescope, right? You're looking at, say, $1 billion to send up astronauts to make some fixes to the Hubble Space Telescope. And that makes sense if your telescope is going to cost you, say, $10 billion, like, I don't know, James Webb. But for most of their telescopes, the cost of just launching a brand new telescope is less than servicing it, sending up astronauts to resupply it. Now, there have been some ideas about putting some kind of observatories on the International Space Station. And there is an X-ray observatory on the International Space Station called NICER, the Neutron Star Interior Crust. I forget what it's called. But anyway, NICER. We talk about it in an upcoming episode. So there are certain kinds of instruments that do make sense to apply to the space station, but a great big optical telescope, I think you launch it as a telescope. And I think the future is you build them in space out of robots that assemble the whole telescope in some perfect location, completely unconnected from human beings. We're not super useful in space is the problem, right? We're made of meat, and we're soft, and we're squishy, and we can't handle a lot of extremes, and we need to eat, and we need to poop, and we got all these problems, so just turn them into robots. Chris M. What would be the best viable real-world way to reduce light pollution? I live in Northern California, and light pollution makes it extremely difficult to appreciate the night sky. However, I've taken trips to Texas, Arizona, Tennessee, and felt mesmerized by the views. Sedona, Arizona, has an interesting take on this. Can this be replicated nationwide? So what you're talking about is the idea of cities taking their night skies very seriously and across the board measures that will reduce the amount of light pollution that's going off into sky. And a lot of times, we have these lights, these street lights and building lights that are illuminating, and they're pointing their lights up into the sky. And that serves no purpose. It wastes electricity, and it illuminates and destroys the night sky. And anybody who has spent any time with truly dark night skies, they've seen the Milky Way, they've seen how bright the stars are, you know what a tragedy it is for the people who live in these cities, and they have never experienced it. And I'm sure there's a bunch of you who are watching this now who you've never seen the Milky Way with your own eyes. You've never been to these really true dark skies. And the first step, I think, is most people should like go on an adventure, take yourself to a place that you can see the night sky. I know the people in Europe, it's pretty hard. Like if you live in the Netherlands or Belgium, there's like almost nowhere that you can go. But even if you live in, say, the eastern United States, there are some places you can go and be able to see the Milky Way within a couple of hour drive. I mean, in order to take this farther, we've got to have cities take this very seriously and appreciate the fact that they're losing their night skies, they've lost their night skies, and that there is something really wonderful to be connected to the stars. And it's not that expensive, and it's not that complicated, and especially as we are transitioning over to these worlds of LED lights that can direct the light in very specific ways. You can change the colors to be the right kind of light color so that it doesn't affect the skies. There are some associations that are trying to do this work, so maybe you may want to participate. The Dark Sky Association, I think, is one of them, and there are dark sky parks that you can visit. So it's a tough problem. I wish people took it seriously, and I don't know what the solution is except to everyone be the mayor of your town and then sneak in the legislation to make sure that the city lights are dark sky appropriate. Manly Mencesis. If we change just one variable about Earth's habitability, like if Earth was tidally locked to the sun, still being 1 AU from it, what would it be like? Just how fragile is life? This is a tough question because we only have one sample of a place that has life in the universe, and that's Earth. And so we know that the Earth is the right distance away from the star for water to be liquid. We know that the mass of the Earth, that we have a big enough planet to have plate tectonics, and we have a still fairly liquid core with the rotating iron core that creates a magnetic field that protects us and protects our atmosphere. We get a certain amount of illumination of the right kind of photons from the sun. So we've got the right kind of star, right kind of distance, right kind of planet, made of the right materials. We think that the moon had some kind of impact in the habitability of the Earth. So there's this idea of the Drake equation, right, where you've got various factors that account for life being able to form on a planet. And the reality is that there are probably hundreds of those factors, some of which are deal killers. Like if you don't have a geomagnetic field, if you don't have a main sequence star that's not blasting out killer flares, if you don't have a large moon, then life just cannot form. Or maybe life can form just on the edges. So if you had a planet that was tidally locked to its star, as you mentioned, it only shows one face to the star. Then the one side of the planet will be scorching hot. The other side of the planet will be frigid. You'll get some temperature moving around because of the atmosphere, and you'll have this really thin margin along the sides, the terminator, where temperatures might be appropriate for life to be able to survive. So we kind of just don't know. We don't know what all the variables are, and we won't know until we find more examples of other planetary worlds. And we go, hey, this place has got a big moon just like the Earth, but it doesn't have life. Or we found a place that does have life and it doesn't have a moon, so moons aren't necessary. More research is needed for us to figure this out. This is kind of what makes it so exciting. This is what makes exoplanetary astronomers, the people finding these new planets, get up every day, is they want to know the answers to these questions. Devo. Can a star and a black hole orbit each other and create a really weird binary system thing? They absolutely can. In fact, this is the way that astronomers have found black holes in the past. Because a black hole, right, is so powerful, so dense that nothing, not even light, can escape its pull. And so how do you see something that is invisible? And you don't, right? You can maybe detect if it's got some kind of disk of material that's swirling around it, and that's when it's got some other star that it's feeding off of. And so you get this situation where maybe back in the day there was like a really massive star and then maybe a smaller star like the sun. And the two stars were in a binary system around each other, and then the really massive star exploded as a supernova and then collapsed down as a black hole. And now you've got a black hole and a star like the sun orbiting around each other. And so material swirls off the star and goes into an accretion disk around the black hole. So it's like this disk of material that builds up around the black hole because it's like too much material for the black hole to be able to eat. And so it piles up like water swirling around your drain. And that gives off illumination, that gives off light. And so astronomers are able to detect this. As well, if you've got, say, the black hole and the star in a sort of a plane where they're passing in front of each other from our field of view, then the light from the star is going to change as the black hole is passing in front. So you get some really interesting situations. So yeah, it can absolutely happen. And there are plenty of these examples out there. X-ray binaries, I think they're called. And I would love to be able to see one of these up close. Can you imagine what it would look like with a black hole and a star swirling around and this? I'm sure Chad's going to put up a really cool picture to show you, or an animation to show you what it'll look like. But it's a scenario that happens out there. Christopher Harstad. Hey Fraser, so how does time go slower in high speed, even if that speed is in a circle around the Earth? I don't understand this. You travel and come back to the same point, but you've spent less time doing it than someone just waiting there? Yeah, so explain time dilation, Fraser. No problem. So here's the thing. The thing that Einstein figured out, the thing that changed our understanding of the way the universe works, is that he figured out that the speed of light is always the speed of light in a vacuum to every observer all the time. And it doesn't matter how fast you're going. So if you're going, I don't know, let's imagine here, you got two cars coming towards each other, right? And you're going 100 kilometers an hour and the other car is going 100 kilometers an hour and you're coming towards each other, then from your perspective, you're seeing that other car come at you at 200 kilometers per hour. And from their perspective, they're seeing that car come at them at 200 kilometers per hour. Now, if you shine a flashlight from one car to the other car, right? One car sees the flashlight and the light is coming at them at 300,000 kilometers a second, and the other person sees the flashlight coming at them at 300,000 kilometers per second. It doesn't seem like it's a big number. But let's imagine that they're spacecraft and they are going 99.9% the speed of light towards each other. So one shines the flashlight and they see the light going 300,000 kilometers a second. So does the other person. And so no matter how fast you think that you're going, the light is always going the same speed. And so then the question is, how can light go the same speed? Because you're definitely moving, and the only way is if time is willing to change. So I'll give you sort of the thought experiment that really hammered it home for me is you imagine that there is a train that's going past you, right? And there's somebody standing in the train and they are, say, bouncing a ball inside of the train. And so as the train is going past, you're watching the ball do this sort of V shape diagonal line. It's going up and down as it's going past, right? So for the person inside the train, they're bouncing the ball and they see the ball every time it's making, say it does two meters. So it goes 2 meters for each one of the times that they bounce it. But for you outside, as you watch this ball go past, the ball is actually doing a longer journey. The ball is doing, say, I don't know, Pythagoras, like 3 meters, right? 2 squared, I should get this right? 2 squared, 4 plus 4, 8, square root of 8, like almost 3 meters. So you're seeing the ball, but your perspective is the ball has moved 3 meters. Their perspective is the ball has moved 2 meters. And that makes sense because we know that things that are moving faster, you think the ball can move faster. But in the terms of light, from your perspective inside the train, say the light is going 300,000 kilometers per second. From my perspective outside, the light is going 300,000 kilometers per second, but I'm seeing a longer journey. And the only way that's possible is that if me and you, the person inside the train, are experiencing different amounts of time, because the speed always has to be the same. So I hope that helps. I know it's mind-bending, but it's the way our universe works. And because the speed of light is always constant. in a vacuum. Save the emails. Kevin Slade. If the SpaceX BFR or Starship is successfully developed, it is claimed that it will be able to launch 100 to 125 metric tons to low Earth orbit, or 30 to 40 metric tons to geostationary orbit. Furthermore, the cost, not necessarily the price of the payload, for these launches is said to be possibly as low as $50 to $100 per kilogram. If this turns out to be true, then due to this new enabler, a new market for space-based services is likely to quickly develop, just as the lowering cost and ubiquity of internet services made applications like YouTube, Netflix, and Facebook possible. So what are the most likely business and science applications that will take advantage of the new lower cost space launch market that Starship and its likely future competitors will enable? So those are some big ifs, right? If the Starship launches. We saw the Starhopper tested, it came up, moved sideways. So I think we're on our way. I like to give Elon Musk the benefit of the doubt. So maybe in the next decade, we'll see Starship launch. I know it's going to be next year, but things take a little longer than we expect. So the price, right? That's crazy, $50 to $100 per kilogram. And that is, on the low end, cheaper than the price of a space elevator. So, like, if they can perfect this technology, the idea of a space elevator is now out the window. Who cares, right? You don't need to build a space elevator because reusable rockets are much cheaper. So then what do you launch? It's still kind of expensive. Even, let's say you want to launch a 1-ton satellite, 1,000 kilograms. It's going to cost you $100,000 to launch it, which is pretty cheap. I could do that. A bunch of our friends build our own satellite. So though that's the kind of math that people are going to be thinking about. They're going to be saying, oh, I could do that. I could build a satellite and launch it into space. And of course, the size of satellites are going to come down. I think that if this does happen, and I've mentioned this previously, and this is where my mind is going right now, is that we are in this transitionary period between a Earth economy that launches stuff to space to a space economy that makes its own stuff in space. And that there will only be a few, probably decades at the most, where we're going to need to launch stuff off of the Earth and out into space. And we could do it just with Falcon 9s. You launch self-replicating robot factories, machines capable of dismantling asteroids, manufacturing systems in space. And then after a while, you just don't need to launch anything from the Earth anymore, except for maybe people who want to go off to space. Everything else is built, harvested, done in space. So I think we're going to have this, in the short term, we're going to get all of these satellite constellations. They're all going to go up really quickly. And then we're going to get the space-based manufacturing infrastructure that's going to get launched. It's going to be factories are going to be sent to space. And then the factories will be capable of making more factories. And so the necessity of these launch systems will die down. And I think that we are, like I said, I'd say 50 years of we were the times when we needed to launch a lot of rockets, and then we won't need to do that anymore. So it's a really interesting time. I think we are in this really fascinating moment in history that obviously will never be repeated. And I'm interested to see how it all plays out. It's great to be watching it unfold year after year in real time. Together, let's keep watching. Stress test punk rock. Question: how do galaxies collide when everything is expanding? The galaxies all drift away from each other. Almost everything is expanding. So at the large scale, when you look at galaxies that are billions of light years away, hundreds of millions of light years away, they are all expanding away from each other at this really even amount, the Hubble constant. And over the larger scale, this is what we see in all directions. Galaxies are moving away from us. But at local levels, so say us and Andromeda. Andromeda is only 2.5 million light years away. Triangulum, all of the galaxies in the local group, they are attracting each other with their gravity. And at the small scale, the amount that they're attracting each other with their gravity is more than the expansion of the entire universe. So at small places, and by small I mean the local group, the tens of millions of light years across, the local gravity is what's strong. But over the large scales, it's the expansion that's carrying everything away. But eventually, over time, all of the galaxies that are in our local group will cluster all together into one mega galaxy, and all the other galaxies will just fade away and fall over the cosmic horizon and be gone forever from our perspective. So that's how it works. Fernanda Bacher. Hey Fraser, love your channel very much. I know that Saturn's rings are disappearing. Can we blame the sun for this? I mean, the rings are made of ice and dust particles, right? So does it evaporate every time the planets get closer to our star? There's a region in our solar system called the frost line, and this is the place where ice sublimates away because of the radiation that's coming from the sun. And that region is halfway through the asteroid belt. So Mercury, Venus, Earth, Mars, half of the asteroid belt, any water, if you leave out an ice cube on any one of those worlds, the sun's radiation will blast it away into space. It'll sublimate and be gone. Except for the Earth, we're protected by our magnetosphere and our atmosphere, so we get to keep our water. Once you move outside the asteroid belt and farther out into the solar system, say to Jupiter, to Saturn, Pluto, everything, then water can't exist because the radiation just isn't strong enough that far out into the solar system. And Jupiter has all these icy moons. It's got Europa and Ganymede, right? And they are covered in ice, and Callisto. And then Saturn, of course, has lots of icy objects. It's got Enceladus, and its rings, as you say, are made of ice. So it's not the radiation from the sun that is making Saturn's rings go away. What it is that the particles of the rings are being pulled into Saturn itself. So Saturn is eating its own rings, and it's assisted by the moons that are going around as they're sort of causing disturbances in the ring particles. And now it looks like the rings are going to be gone within the next tens of millions, hundreds of millions of years. So astronomers have been able to fairly recently discover that the rings are probably fairly recent, caused by maybe a breakup of a moon or caused by a comet or being torn apart, and we get to see them. It's like really fortunate that we get to see them now, and they are going away and they will eventually be gone, and Saturn will kind of look like Jupiter, but without rings. Without icy rings, anyway. Maybe they'll also have dirt rings like Jupiter and Uranus and Neptune do. But it's amazing, and it's kind of sad. So, all right. Well, those are the questions this week. Thank you, everybody who put in your questions. As always, wherever you are, anywhere across my channel, if a question pops in your brain, write it down. I'll gather them up. I'll answer them here, and I'll see you next week.